Hello everyone, my name is Mark and I'm going to be starting my group strategy plan for our large language model project that solves mazes. So a quick little project overview. Our project aims to build a large language model, LLM, that can solve mazes using the A-star shortest path algorithm. We'll explore how the LLM can integrate structured algorithms to enhance problem solving capabilities. And overall, our goal is to explore whether an LLM can understand and apply a structured search algorithm such as the A star to various pathfinding problems. And our approach will include training the LLM to understand maze layouts, such as the start, goal, walls, and other obstacles it might encounter. We'll be teaching it to apply this A star algorithm, and then we'll be comparing the results with the traditional A star pathfinding algorithm to see how well it performs. So what is the A star algorithm? The A star algorithm is a widely used pathfinding algorithm. It finds the shortest path between a starting point and a goal, and it's used in many games, robotic applications, and navigation systems. And overall, it helps AI make smarter decisions rather than random guesses. So how we'll be using this A star algorithm in our project? We'll be using and training our LLM to understand maze-like structures using this algorithm to solve mazes. So instead of manually coding the A star into the AI, we'll see if our large language model can learn and execute it based on the provided instructions and examples. And this is very important and it matters because traditional pathfinding algorithms such as the A star are very rule-based and predictable. However, large language models can learn and adapt, which is very important because they dynamically learn and adapt. So the model will generate generate paths and will compare its results to a standard A star implementation. We will then test whether the LLM can apply the A star correctly, adapt it to different types of mazes, and improve over time. So why use an LLM? As we've discussed and learned throughout the course, LLMs have demonstrated strong problem-solving capabilities. And as I said in the previous slide, traditional algorithms such as the A star follow strict rules, while LLMs can learn and adapt. And LLMs will be able to understand different types of mazes beyond just simple grids. And A star is also precise. However, LLMs can handle situations where information is missing or uncertain. For example, in our game, in our puzzle, in our project, we might encounter partially blocked mazes or obstacles, which is where an LLM can come in. So overall, our project goals is to develop an LLM that understands and executes the A star pathfinding algorithm correctly, precisely, and accurately. We will then compare the LLM's performance with the traditional A star pathfinding implementation to evaluate the speed and efficiency and accuracy. We will then optimize the large language model's ability to reason through these tasks. And hopefully at the end of our project, we will be able to identify and address limitations in how large language models understand and execute such algorithms such as the A star.
Okay, so our expected project outcome. We want to create a working LLM that completes its job as intended and is able to adapt to new and different kinds of data. The way that we will make this happen is we will have to start comparing our model that we create to others that have been made before and see if we're performing efficiently or if our model is taking too long to solve the mazes. We want our model to be able to solve these mazes with the most efficient path, but also to see how long it usually takes a model to solve the maze. They will be turned into a format that we will create using a smart AI model that will teach it how to solve the mazes. The way that it'll learn would be through looking at example mazes and then figuring out which is the best possible way to get through these mazes. And we'll proceed to make it better by seeing how it performs with certain mazes and then gradually improve it as it moves on to bigger and more complex mazes. At the end of this project, we want to be able to have a working program slash website that can show how our LLM works, and so you can see it in action, because that way other people can try out with different mazes and see how quick or how slow our model will solve the mazes that are provided to them. Our methodology and approach. So our approach is going to be collecting and preparing lots and lots of maze data. So with a different maze that pops up, we will mark how fast or how slow, whether it picked the best approach or the second best or the third best, and see how it performs with different types of mazes. Also, we will be training the model so that it can solve the mazes more efficiently. So solving a maze is one thing, but being able to solve it efficiently makes it a better model. And then as the LLM begins to improve on the types of mazes that it is solving, we will be adding more difficult mazes as it progresses to see if there's any improvement with the model. And we want to make it better. We want to make sure that the model doesn't crash with certain kinds of mazes. Like if there's a maze with no exit, we want to make sure that it can handle that approach and not completely crash the program. We want to make sure that it understands that there could be a maze with an exit, there could be a maze without it, but at the end of the day, reaching from one point to another can also be seen as a type of reaching from beginning to the end of the maze. And so that is our approach that we are going to take when creating this model for a maze. We believe that it is the best approach because it allows the AI model to practice over and over and over and over again so that it can improve on what it already knows and for it to deal with more difficult problems later on.
Okay, so tools and technologies. So our primary language for this project is going to be Python. It's a great choice for implementing pathfinding algorithms like A*STAR because of its simplicity and powerful libraries for numerical computing and visualization. To represent and process the maze, we're going to use NumPy. NumPy makes it easy to manipulate and analyze the maze structure efficiently. Each cell in a grid represents a wall, an open path, the start, or the goal. Now for our pathfinding algorithm, as explained earlier in this presentation, it's going to be A*STAR. Now what we're thinking about is most likely this is going to be constructed with priority queues, a heuristic function to estimate the remaining distances, whether it's the Manhattan or the Euclidean distance, and obviously a cost function to track the shortest path. Now for visualization tools and UI, We're thinking about using Matplotlib. This is a library to create simple 2D representations of the maze and the AI's path. Um, so by combining Python, NumPy for processing, and visualization tools like Matplotlib, we're building an efficient and interactive maze solver. Our goal is to showcase A star as an intelligent and optimized approach to pathfinding. Now, my role is the UI and visualization developer, right? So once the AI learns, we need a way to see its progress. That's where I come in. My job is to create a visual representation of the maze and how the AI moves through it. Like I said, I may use Matplotlib to show the AI's learning process. Um, this is important because visualization helps us understand if our model is actually improving. Right? If we can't see it, then we don't know what's going on. A crucial role in our project is the algorithm and pathfinding researcher, which will be my partner Kareem. This person is responsible for studying, understanding, and analyzing the best approach for solving mazes efficiently. Now, we will all be doing this to some degree, but Kareem has been the one appointed to really go in depth and research as much as he can about the algorithm that we will be using. Alright, now another key role in our project is the maze generation and environment developer. This role has been entrusted to our partner Kevin. This person is responsible for creating the mazes our AI will navigate and ensure that the environment is properly structured for testing. Now, to go in a little bit more depth, the AI needs different types of mazes to test its performance. By generating a variety of mazes, we can test how well the AI adapts to different layouts. The mazes have to be well structured. We have to make sure that there are no loops, there are no dead ends. Our AI is scalable, right? So that means that it can solve a little maze, it can solve a big maze. Now one of our most important roles in our project is the testing and performance analyst. This role falls upon Mark. This person ensures that our maze solving AI is accurate, efficient, and performs well across different scenarios. Essentially, what Mark will do is that verify that our AI is solving mazes correctly. Right? He will test the simple mazes, he will test the complex mazes, ones that may have like dead ends or something, our large mazes. This can be used to measure performance under high complexities, right? Mark can also measure our performances, right, or the performance of the AI via execution time, the path efficiency. This means whether or not the AI actually takes the shortest route, things like memory usage, things like the success rate, right? So how often it reaches the goal in different mazes. Another thing could be debugging, optimizing the system, identifying bugs, like I said, inefficiencies, optimizing data structures that we use that might be slowing it down. At the end of the day, Mark is ensuring that our maze solver runs smoothly and efficiently.
Let's go over some of the key challenges we expect to face in this project. First, one of the biggest challenges is encoding the maze in a way that both the LLM and A-star algorithm can understand. The maze needs to be represented as a structured format, typically a gridded graph where nodes, paths, and obstacles are clearly defined. If the encoding is inefficient or inconsistent, it can lead to errors in navigation and pathfinding. Next, we need to ensure that the LLM has a proper conceptual understanding of the A-star algorithm. Since A-star relies on heuristics and path cost calculations, the LLM must apply these correctly rather than relying purely on pattern recognition. A key challenge is determining how much the LLM needs to reason about the algorithm versus following explicit programmed instructions. Another challenge is how we represent the state of the maze and track progress through it. A large or complex maze could quickly lead to high memory usage, especially if the LLM needs to store multiple possible paths. Managing memory efficiently while keeping track of visited nodes and potential paths will be crucial. Even if the LLM can generate a solution, we need to understand that it does so efficiently. A-star is an already optimized algorithm, but incorporating an LLM could introduce overhead. We must balance computational costs with solution speed and avoid unnecessary calculations that slow down performance. Finally, we need to ensure that the solutions generated are truly optimal. A-star guarantees an optimal path under the right conditions, but if the LLM misinterprets the heuristic function or applies faulty logic, it could produce suboptimal paths. Verifying output correctness and debugging any inconsistencies will be an ongoing challenge. Now let's discuss how we'll evaluate the performance of our LLM-powered maze solver. One of the key measures of performance is execution time. How fast our system can compute a solution. Since A-star is designed to be efficient, we need to ensure that incorporating an LLM doesn't significantly slow it down. Another critical factor is memory consumption. The more nodes we store and process, the higher the memory requirements. We'll monitor how our system handles large mazes and whether the LLM introduces unnecessary overhead. A-star guarantees the shortest path when implemented correctly. We will compare the LLM generated paths to standard A-star paths to verify optimality. Efficiency can also be measured by the number of nodes the algorithm expands before reaching the goal. Ideally, the LLM should not increase the number of expanded nodes beyond what a traditional A-star search would do. To evaluate reliability, we'll measure the percentage of mazes where the LLM successfully finds a valid path. A consistently high success rate indicates robustness. Finally, we need to test the system with a variety of maze sizes and complexities. A strong model should be able to generalize across different scenarios without performance dropping drastically. Now that we've discussed our evaluation metrics, let's explore some real-world applications of an LLM-powered A-star solver. One of the most prominent applications is in robotics and autonomous navigation. Robots and self-driving vehicles use pathfinding algorithms like A-star to navigate dynamic environments. An LLM-enhanced approach could help robots interpret complex terrains, adapt to obstacles, and make intelligent routing decisions based beyond traditional algorithms. In gaming, A-star is widely used for NPC movement and enemy pathfinding. Integrating an LLM could allow for more human-like decision-making, adapting strategies in real time based on the player's actions rather than just following pre-computed paths. Another crucial application is in search and rescue. Drones or robots navigating disaster zones must quickly find the safest and fastest route to reach trapped individuals. An LLM-powered A-star could enhance adaptability in unpredictable terrains, making navigation more effective in real-world emergency situations. Beyond physical navigation, A-star is also used in network routing to determine the fastest path for data packets across networks. An LLM-enhanced system could optimize real-time traffic management in large-scale networks, reducing congestion and improving efficiency. The first phase focuses on on understanding how to integrate an LLM with the A-star algorithm. During the research and planning period, we will review existing literature, explore relevant frameworks, and finalize our approach to maze representation and state management. Once the research is complete, we will begin building an initial prototype. This includes implementing the A-star algorithm, connecting it with the LLM, and running basic tests to ensure it correctly interprets and solves the mazes. During the refinement stage, we will fine-tune our system by optimizing execution time, memory usage, and overall performance. We will also conduct an extensive testing with different maze sizes and complexities to improve robustness. In the final phase, we will complete all testing, document our findings, and prepare for the project presentation.
All right. Our project focuses on developing a large language model or an LLM that can solve mazes using a shortest path algorithm. And the main goal is to explore whether LLMs can integrate structured algorithms and apply them effectively to problem-solving tasks. To do this, we're taking a structured approach. First, we'll train the LLM to recognize and understand the maze layouts. This includes identifying key elements like the start position, the goal, some walls, and even the paths. Then we'll teach it how to apply the A algorithm using heuristics such as Manhattan or Euclidean distance to determine the shortest path. To measure its effectiveness, we'll compare the LLM's performance against a traditional A implementation. We want to see how well it can navigate differently with maze complexities and how accurately it follows the algorithms, and whether or not it can generalize new or unseen mazes. And then this is our different approaches continued. To beyond just solving mazes, we'll also analyze the LLM's strengths and weaknesses, such as does it struggle with memory constraints, does it come or sometimes generate incorrect paths, and how can we improve its reasoning. We'll explore different techniques like fine-tuning, reinforcement learning, and even prompt engineering to enhance its problem-solving capabilities. Ultimately, this project will help us understand if LLMs can go beyond language tasks and even effectively apply structured algorithms. If successful, this could open doors to new AI applications in areas like robotics, game development, and even automated design.